2004, she's a research scientist at the Instituto de Astrofísica de las Canarias, IAC, in Spain. Her work focuses on solar physics, MHD wave theory, partially ionized plasmas, and spectropolarimetry. So welcome, Dr. Elena, and please join us.
Okay, thank you. Thank you very much for inviting me. Shall I share my screen now?
Yes.
Okay, I will do so. I can share my slides. Thank you very much. I'm excited about this experience. So let me see if I can explain myself and explain what actually I'm doing from my everyday.
It has been, I'm pretty sure it's a lot. We have been reading about you and all the different research that you do. And we can't wait to hear you. So, okay, I will leave the floor to you. And afterwards, we will have a couple of questions. So if anyone on the audience would like to ask questions, you can do it in the chat and we will ask directly to Dr. Elena after her talk. So thank you.
Okay, then. So let's go into it. Okay, so since the subject of all this group of talks is about the sun, I will not be different. So I will be talking about my favorite object, which is the sun. And in particular, I will be talking about the solar atmosphere, which is one of the regions that we can actually observe by the naked eye. So I start from very far away. We know that sun is one of the stars in our galaxy. So what we see here is an image of a galaxy cluster observed time ago by Hubble Space Telescope, and it shows us a set of different galaxies, right? And sun, as many other stars, which are ordinary stars, or some of them are peculiar stars, they're formed in galaxies. They're part of our galaxy. So there are millions and millions of stars in each of these galaxies that we see here in this image, and one of them can be our sun. Except that we cannot see our galaxy, of course, because we are inside it, so we cannot see it from outside, right? So we see galaxies which are far away. So the sun, it's born from a molecular cloud, with dust cloud, in such an environment, such as a galaxy, okay? And then inside this proper galaxy, the sun is located at the suburbs of our Milky Way. So again, this is not a real image of our Milky Way galaxy, but this is how it could look like in principle. So this is an artist's impression of the Milky Way galaxy. And luckily, the sun is located not at the center where we might have a black hole, and not very far in the suburbs where we can be radiated by cosmic rays. Sun is located in the suburbs. And this is like living in the suburbs of a big city. So it's still close to all this energy and environment, but it's sufficiently quiet so the life can develop around the sun. And thanks to that, thanks to this peculiar location of the sun in our galaxy, we can actually have life on our planet. And then, if we continue approaching, the sun might have been born in a molecular cloud similar to the one as we see here. So yet again, this is a spectacular image from the Hubble Space Telescope of an open young cluster in a small Magellanic cloud that one can observe from the southern hemisphere. And it shows us a myriads of young stars. So when the sun was born, it was born from a material which already belonged to a star which was already in this place. It went through the process of nuclear synthesis and explosion, and then this material has been recycled, and then our star has been formed. And after that, so the sun has been formed, and then it arrived to the main sequence of what we call the main sequence of when we classify all the stars that we know. And therefore, the sun, there's at least several reasons to study the sun, and all of them are equally important for me, but probably one is the most important because I'm mostly a plasma physicist and not an astronomer. So I will come to this later. But so far, we can tell that sun is a reference star for astrophysics. And this is so because all the stars that we know in the universe, we classify in the galaxy, we classify them in terms of what we call this Hertzsprung-Russell diagram, where we locate them as a function of their luminosity and of the function of their temperature. And then we know that all the ordinary stars, they essentially appear along this main sequence. And sorry for this being said in Spanish. And then there are also locations like peculiar sets of stars of red and blue supergiants, and also black dwarfs, and some other stars which are even not placed here. Okay, so the sun is located right in the middle of this diagram, and this is so because every star that we measure with respect to the sun. We measure with respect to solar abundances, we measure with respect to solar luminosity, we measure with respect to solar temperature. So if we normalize everything to the sun will be just one in the units of the sun. And therefore, it's so important to have a precise information about the sun, about the abundances, about how the processes are inside the sun, and also in the solar atmosphere, how there are coronal mass ejections, and so on, because it's a reference for the rest of the astrophysics. And then another reason to study the sun is because it's a huge physics laboratory. The conditions that we have inside the sun, they cannot be reached in the Earth. And this is good because it's very, very hot inside the sun. So what we see in this picture is again, an artistic representation of what the sun could be if we just cut through its surface. And unlike a planet, for example, a planet that we live on, it doesn't have a solid surface. It has a core where all the nuclear reactions take place and where we burn hydrogen into helium. And the core temperature are about 15 million degrees. And then this energy, which is produced in the core, it is transported in terms of radiation through the radiative zone. And then it takes millions and millions of years of one photon, one element of light to actually exit this radiative zone. And this is because it's so dense. So every single photon is getting absorbed and re-emitted millions and billions of times before it can actually reach the surface. So the light that we see from the sun, it has been produced like in millions and millions of years ago. And then when eventually this light, this energy is able to reach this layer that is marked like red here between the convective zone and radiative zone. So we enter the convective zone, and this is the zone where the main energy transport mechanism is the convection. It's a plasma, it's a solar gas, is boiling because it's getting heat from below and then it's getting cooled on the surface. So it's like boiling something in a pot. And there the energy transportation is very, very fast because it's a fast transporting mechanism. And now we are reaching the surface. And what we call the surface, the definition of the surface, it's called photosphere. The right definition of the surface is because where the light gets emitted. So everything which is below the surface, we cannot see. We can only infer this information indirectly. And everything which is a photosphere and above this one, we can actually see because the photons, the light, can actually escape, and we can measure it through our telescopes. And then there are several regions in the solar atmosphere, which we call photosphere, chromosphere, transition region, and corona. The last one, corona, is hugely extended. And all these regions, they are shaped by the magnetic field. Because what makes sun interesting, and in particular, it's very interesting to me as a plasma physicist, is a magnetic field. So this is what makes a difference between the gas and the plasma, the presence of the magnetic field. So this shape of the solar corona that we see, this is thanks to the presence of these invisible magnetic field lines, which actually make the plasma to be structured around it and form loops, form streamers, form prominences, and other structures that we observe from the sun. And then, of course, and this is what is concerning everybody here on this planet. Sun is the closest star that we can actually have. So any other stars are at least several light years away, and this one is close to us. So we only receive the light from the sun at about 8 minutes after it has been emitted from the sun. And then also there are energetic particles and everything related to when there are some coronal mass ejections, mass is ejected from the sun and reaching the Earth. And what we see here again, it's an artistic representation of when there is a coronal mass ejection, a mass ejected from the sun because of these violent eruptions related to the magnetic field. And when it reaches the Earth, it encounters a shield of the Earth's magnetic field. And again, magnetic field is essential here because it protects our planet from this external radiation. And if we talk about magnetic fields, so for example, in finding extrasolar planets, it's essential to know if they have or not the magnetic field. Because, for example, Mars has very weak magnetic field. It means that it is not protected from sunstorms. And therefore, probably life on such a planet could be much tougher than on the Earth, because these ultraviolet radiations, these very fast particles, they can be killing for life, and essentially they are very much killing for us as a civilization, and that we know that. And therefore, it's very essential to study sun and study sun's magnetic activity and understand these violent eruptions and how they affect our Earth's environment. So how do we how do we study the sun? The information that we receive from the sun is what we see here on this picture. So this is a solar spectrum. Solar spectrum is a rainbow. It's when you, for example, receive a light beam from the sun and you put a prisma, and then you see that your light is split into the rainbow. But the solar rainbow is not just a rainbow as in any stellar spectrum. Stellar rainbow is not just simple division in colors. What you see here is these black stripes all over the place. And these stripes, we call them spectral lines. Spectral lines are fingerprints of different chemical elements which are present in the plasma that emits this kind of light. So these chemical elements are sitting there somewhere in the photosphere, in the atmosphere of the sun. And when a light of a given color reaches these elements absorb this light. And from how big is the spectral line, actually how thick is this black stripe, we can guess actually how many of these elements are present, what is their abundance. And spectral lines give us all the information we have about the sun. Not only this, but also we need magnetic information is given when this spectral information as the light is polarized. Okay, so it's difficult to explain, but then when it's electric vector is not oscillating like randomly, but it's oscillating around a given direction, then we also get a magnetic information. But just from mere spectral lines, we obtain most of the things we know about the solar composition, the solar temperature, and the solar velocities, and like that. So how do we do this? So what is a spectral line? Spectral lines, it's something looking like this. So this is something which might seem to you rather boring, because this is a mathematical curve, which is a Gaussian, inverted Gaussian. So I plotted this like an inverted Gaussian. So it's not like a single stripe, single delta function. It has an extension. And from this extension, from the thickness of the spectral line, so it can become thicker or it can become thinner. And for example, from its extension, we can guess about the temperature of the plasma, and we can guess about something we call microturbulent velocity. So how vigorous is a plasma motion on this very small scale that we can observe. And also when the spectral line, for example, is displaced from its laboratory position, we know that it happens because the plasma, the gas in the sun, is moving towards us or moving in the opposite direction. And from that, we can measure the velocities. And then when we can observe the sun at spatial resolution, so we can resolve the surface. So from this, we can restore like maps of the solar surface at different levels. So essentially, everything we know about the sun comes from these spectral lines. And then when we talk about the sun, the frequent misconcept is that from the nighttime astronomy, people say, okay, for the sun, you're lucky because you have all the light you need, so you don't have to build a big telescope to observe the sun because you have a lot of light, right? So light is precious. You obtain light, and from that you analyze, and you get your photons. But this is actually a misconception, because when we observe the sun, we do not obtain light from the whole surface. We are interested in a very small details of the solar surface. So here is the sun, okay, and we are interested in something which is, for example, this is a sunspot, okay? So we throw away every other light which comes outside of the region, which is not the sunspot, which is all this huge light, and actually we have to get rid of this light. Okay? So this light, this is something we're gonna have on our picture, but not only that, because this is composed by many single small pixels. Okay, so what we get actually this image, exaggerating a little bit. So we are interested in these very small pixels because we want to have a surface, we want to have a spatial resolution. So each of these pixels only receives the size of the sun, which is maybe 100 by 100 kilometers small, and everything else has to be thrown away. So we get very little light, and this is what we call the dark sun, because this is what we actually interested in. Everything else we have to throw. And in order to analyze this, because then we the same as stellar astronomy, we lack photons. We need more photons from this. So we need large collecting surfaces. And for that, there is a future project in Europe that Europe is strongly pushing, which is a European Solar Telescope project that is going to be built in the observatory of La Palma here in Canary Islands sometime in the future. So I welcome you to visit the website and to get more information about this telescope. And then again, the luxury of the sun is being able to observe it with all spatial resolution that we can get. Sun is the only star which surface we can get with a spatial resolution, so we can reserve the details. So what I'm going to show you in the next video is then what happens if we have first a solar disk, and then we get closer and closer and closer to the sun. So essentially, it shows on the right, it shows a solar disk rotating, as because it's a body rotating, and then on the right it shows, and I play it again, a small piece of the solar surface when we just get closer and closer and closer to it, like if we would be flying with a drone, for example. And then what we see here is a spectacular picture with his spectacular details that we are not able to get in other stars because of the sun's proximity. So we get the granules, we get all these dark intergranular lanes, which are the manifestation of subsurface convection, of this boiling of the material. And then we also get the bright features, which you can see inside the dark lanes. And also we see these dark spots and also dark filaments. And all these are manifestations of the magnetic field. And we know that not only because we observe this in this light, as we have seen in the image, but also because we observe it in polarimetric, in polarimetry. So we observe it in polarized light. And we know that if light is polarized, then there is a magnetic field producing this polarization. So we measured the magnetic fields in these dark and these bright features, and we know how strong is it. So we can tell about this every detail in the sun in a huge resolution. Okay? But it also brings us a responsibility, because since for the stars we receive very limited information, we just stars are point sources, but the sun has all this spatial resolution. So we get a responsibility to increase the complexity of our theories to be able to explain these interactions. And this essentially comes down to the plasma physics question, because what we see here is interaction of solar plasmas is incandescent gas with a magnetic field, which we call magnetoconvection. Okay, moving next. So this comes back to what is a solar surface. So solar surface is a surface where the light gets emitted and then it reaches us 8 minutes after that, and we obtain this information on the Earth. So what we see here is a temporal evolution of active region of the sun, observed at the Swedish Tower Telescope in La Palma many years ago. And we see here a sunspot, we see here this convection moving, and we see a lot of spectacular activity, but it's probably not so dynamic. So the things are happening slowly here, okay? So we know that there is a magnetic region, there is a sunspot, there are also these little bright details, which are also some small magnetic features moving outside. And this is a level which we call a photosphere. This is a surface. Then if we continue going up in the solar atmosphere, and we move like 1,000 kilometers up, which is not so big. 1,000 kilometers, it's comparable to the, let's say, 1/3 of the Iberian Peninsula. It's not very far away in a distance. So we can imagine this. So only 1,000 kilometers above, we see something like this. And surprisingly, you probably won't tell that just by looking at this image, but surprisingly, what we see before and what we see now is right the same structure. This is the same structure, but this is the same structure seen at level 0 and at level 1000 kilometers, okay? And you see it completely different. And this is what I tell to my students in a solar physics class. So this is a bit technical, but this is a difference between plasma beta above unity and plasma beta below the unity, which is a kind of a plasma parameter which defines you what dominates the motion. It's a gas pressure forces or hydrodynamic forces like pressure, gravity, and forces present in the normal gas, which dominates the motion, or it is a magnetic field which actually dictates the gas, dictates the plasma, how it should move. At the level below, in the photosphere, here, this is dominated by the gas pressure forces, by hydrodynamic forces. So here, plasma moves magnetic features passively. They respond to passive motion, passively to the motion of the plasma, and you can see these bright features, they move with the flow of the plasma. They're like corks. But in the chromosphere, which is 1,000 kilometers above the photosphere, we see the opposite situation. We see that magnetic field already has a lot of strength, and these elongated features, all of them are a manifestation of the presence of the magnetic field lines, strong magnetic field lines here. And then the plasma is forced to move along the magnetic field lines. It doesn't have strength to go against it. And therefore, magnetic field dictates the whole evolution of this region. And this is very interesting because it's not like these two disconnected regions. There is all these different regimes in between and also above it. So we have to study all of this like all together, because otherwise we cannot just understand the system. So it's very complex. So we need to model all this together. And as you can imagine, it also involves very different physical ingredients and very different scales and very different temperatures, densities, magnetic fields, and so on. So, and of course, yeah, we know that sun is the origin of all this activity. So this is again a spectacular image of SDO A and A in ultraviolet, and you see the spectacular explosions that we have there. And this is again thanks to the magnetic field, because at some point it becomes unstable, it explodes, and then it produces coronal mass ejections and prominence eruptions, and so on. So, and now finally I'm coming to the subject of my research, which is about the solar chromosphere, which was a region that we have just seen, which was dominated by the magnetic forces. So chromosphere is sometimes called the purgatory of solar physics. And this is so because in the chromosphere, you cannot make many assumptions. So you have to complicate the theory significantly. So you cannot just say, okay, so my plasma is fully ionized, or my plasma is fully dominated by gas pressure forces, or my plasma is transparent to radiation, or my plasma is fully opaque to radiation. In the chromosphere, everything is like on the same order of magnitude. So you have to take into account basically all the processes that we know there. So chromosphere is known as a region where we have a chromospheric temperature increase. And I explain it here through this figure. So we have the source of solar energy, which is the solar core. And as we move through the regions of the solar atmosphere, through the radiative zone, through the convection zone, and to the photosphere, we move away from the source of the energy. And therefore, the temperature in the normal conditions, it should just go slower and slowly to the bottom. It should decrease, right? Because you're moving from the source of energy. But observations of spectral lines in the solar chromosphere and in corona are an emission. Spectral lines are an emission, and it tells us that there is no equilibrium, that there is no radiative equilibrium, and the temperature is actually not decreasing with height, but it's actually increasing with height. And this we call the problem of chromosphere and temperature increase. And this needs to be explained. So this deviation between the black curve and between the green curve, it needs to be explained. So if there are additional energy, so there has to be the source of this additional energy. And since we know that radiation cannot be responsible for that, because radiation produces the green curve, there must be some other source of energy to move from green to black. And we know that must be something related to the magnetic energy, because magnetic field, it has infinite energy. It has a lot of energy. So if we are able to extract just a little bit of it and convert it into the heat, then we would probably produce something from here to here. And then we also know that the chromosphere is made of different sorts of fluids, which are difficult chemical elements, but it also different atoms in different degrees of ionization. Chromosphere has a lot of neutral hydrogen, and therefore it's called chromosphere. Therefore, we have this red light because it's emitted by the neutral hydrogen spectral line in H alpha 6563 angstroms. But also chromosphere has iron, it has carbon, it has helium, it has hydrogen ions, it has electrons to balance all these positive ions. So it has all these chemical species. And the conditions in the chromosphere, as I said, they are not in equilibrium. So it means that all the ionized species, they are kind of moving all together like a single fluid in general, in very general terms. But then the neutral fluid, neutral hydrogen, is not moving like this, is not related to the rest of the fluid, because the particles are not colliding fast enough. They're not colliding enough to maintain this like a single moving fluid. And the consequences of this are actually extremely important for the problem of chromospheric heating, as I believe and as I study in my research. So what happens that in the photosphere, being in the photosphere is like being in a sunny day on the beach. So you see it on the beach, you see the shadow and you see it in the sun. And then you have a warm wind coming, and then you have also solar radiation, more or less the same temperature as the wind. So everything is very pleasant. So even if the sun goes away, so you still have this very pleasant and hot air, and you don't feel any discomfort. So you're sitting in the photosphere and everything is nice and warm and pleasant. But being in the chromosphere is different. Being in the chromosphere is sitting in a sunny day on the mountain. You get the radiation from the sun, which is hot. So when the sun is shining up to you, you can even take out your jacket and enjoy the sunshine. But once the sun hides behind the mountain, you immediately feel the cold because the air is cold. So it means that the radiation temperature, which is the sun, and the gas temperature, which is the air, they are not the same. And this is right what is happening in the chromosphere. And this is the source of all the problems in modeling that we have in the chromosphere. It's not in equilibrium, not in equilibrium. And then what happens? So we have something which is not in equilibrium. And then we have these fluids which are not fully colliding with each other, so are not fully mixed. And then we also have a magnetic field which forces charged particles to move parallel to the magnetic field. But then we also have neutrals, which they don't care about the magnetic field, because neutrals, they are not charged particles, they're not magnetized, and they are not aware that there is a magnetic field, except when charged particles collide to them. So this situation is very similar to these cartoon pictures we see here. So we can have, for example, like imagine a crowded metro station in the morning. So all these people going to the train, and they want to go inside the train. They are pushing, right? And then there is one, which is this green guy, which can be a neutral, just one, and it's trying not only get away from the train, but it's also trying to push everybody else not getting inside the train. So in order to do this, what do you have to do? You have to collide with everybody very, very fast, okay? Because otherwise, if you're not pushing anybody like very, 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 very fast, you're not able to push the people away from the train. And then what people do, if they are collided with somebody very, very, very fast, people get angry, they get hot, you know. This is exactly what is happening in the chromosphere. We have those neutrals, okay, we have those ions actually, which are green men, which are moved through the magnetic forces. And then we have a lot of neutrals, which are all these people here, which are just don't care about the magnetic forces. And then this little charged particle, it tries to move all the neutrals in the same direction where it is moving. And it actually succeeds to do so, because we have seen in the images of the chromosphere that everything is very much aligned with the magnetic field. It's very difficult to imagine how it really happens, but the sun does it. The sun does it. But in this process, of course, particles collide, and we produce friction, and we produce a heat. And this source of heat might be rather important for the chromospheric heating, because it allows you to extract the energy from the magnetic field and put it into the plasma, into the gas. So In the sun, there are many, in the universe, there are many studies of what we call partially ionized plasma which is partially neutral gas. In the sun, these studies are mostly theoretical. And the reason for that is the following. The reason because the studies are theoretical is because we are talking the processes that happen on very small scales of at least kilometers or below, and temporal scales of seconds. And even with our best telescopes, we cannot reach the scales below 100 kilometers and several seconds. So we need to build bigger and bigger telescope in order to achieve this higher resolution. But so far, we don't have this telescope. And therefore, the processes we can study, we only can study them from the theoretical point of view. And at best, we can hope to make some predictions and then search for them in observations, as I will show later by the end of my talk. And then in order to be able to model this chromosphere theoretically, we need to model the sun in the computer, and we can, of course, solve equations analytically, but essentially, in order to incorporate all the complex processes, we need to solve them in the computer. So my everyday life is solving equations like those that we see here. Horrible, that looks rather complicated. And for that, what is done is we are writing computer code. This code is written in Fortran language, Fortran 90, long time ago. But this is still a good language for the programming. And then, so we solve these equations numerically, we program them into the computer. And then in order to compute the models, we make this code running on a parallel supercomputers like this one in Barcelona. So you cannot model just a piece of the sun in one single in a laptop these days because you don't have enough power. So you have to divide your numerical box into small little details, and then each of them is sent to an individual CPU unit, and then they interact with each other, and eventually you obtain a solar model that may look something like this movie that we see here. So this movie shows us a piece of the sun. We call this model a box in a star because it's a very small box of the sun of the size of 6,000 by 6,000 meters in horizontal and about 3,000 meters in the vertical. So compared to the solar surface, it was just very, very, very tiny region on the solar surface. And we see here some gray stuff, which is the temperature changing somewhere at the bottom level. And then also we see that colorful lines, which are the magnetic field interacting with the plasma. So this kind of models this is what we do like from day to day. And then, as I told you before, the sun is full of the magnetic field. So even outside of the regions which are very prominent magnetic activity, like sunspots and active regions, if we look in the quiet sun, it looks completely boring because we only see granulation if we look in the white light. But if we look at the polarized light, we obtain something like this picture, and we obtain this white and black salt and pepper pattern. And this black and white means that there are locations of the magnetic field. So there is a huge reservoir of the magnetic energy in the sun. And this is something very valuable because from there we can extract the energy, and from there we can extract the energy and bring it up to the chromosphere and to the corona and heat these regions. Okay, so the only question is how to do that. So the question that I'm trying to solve is what are the consequences of this quiet sun magnetic field to the chromospheric energy budget? And then there are two basic processes in the solar atmosphere. One of them, as I told you already, is a magnetoconvection, and this is a process completely analogous of boiling the water in a pot. We get a heat from below, coming from the convection zone and from the radiation zone and from the solar core, and we get a surface where everything is getting irradiated, so the energy escapes, and therefore the surface is getting cooled. So we get a temperature gradient, which is superabatic, and therefore we have this convection, so we have this boiling motion. And this is something we can see in this movie, which I explain later the precedence of the movie. We see this at this small scale pattern, which this movie looks like a swimming pool. So this movie, we see here the velocity obtained with during the first flight of the Sunrise balloon several years ago, many years ago already, and these are so far probably the best resolution observations of this kind of a region. So we see these small scale structures, and these are the granules. These are the boiling solar plasma. But then we not only see the small granules. You may see that we have this kind of water, like a swimming pool effect. So we have a bigger structure. So our eye pick up like a bigger structure, like bigger blinking over this image. And this is what I show here, like by these lines here. These are waves. So when convection stops being the energy transporting mechanisms, these are different kind of waves. And waves are produced by these turbulent convective motions, and then they bring up the energy to the chromosphere and to the corona. So waves and convection, these are two building blocks of the dynamics of the atmosphere of the sun. And talking about waves, we know that in the Earth here, we have acoustic waves. Acoustic waves is something that is needed for me now to talk to you. So these are just compressions of the gas, compressions and rarefications of the gas, and they produce the sound, the music, the voice, the wind, everything that we see here and we hear by our ear. In a magnetized environment, if there is a magnetic field in the plasma, we not only have the acoustic waves, which are purely hydrodynamic, we also have different kind of waves that can be this sausage, king, fast, low magnetoacoustic waves, Alvane. So there's a whole big family of different type of waves, and they combine different forces. So they combine magnetic restoring force, they combine magnetic and hydrodynamic restoring force. So there is a big zoo of different type of waves depending on the shape of the magnetic structures. But these waves, they're not the same in terms of heat in the solar atmosphere. So it's still a current investigation, still a matter of debate, which of these waves are actually more prone to dissipate or which prone to bring energy to different levels of the sun and then dissipate there and to hit which kind of the atmosphere. So we currently do this modeling, including these neutrals and including partial ionization. So we model interaction of the neutral component of the sun with the plasma component of the sun. And we do something like this. Let's see, it's a slow playing movie. So what we see here is again, it's a bit technical. So we see here a piece of the sun, and this is a very, very idealized model. So we see here a piece of the sun of the size of about 2 megameters and by 2 megameters. And the vertical lines is a location of magnetic field lines, and this is a very idealized model. So we send a sound wave from here. So you see here moving in the left lower corner. And we see that this wave reaches the red line. And the red line is where we change from the dominant gas pressure to the dominant magnetic field. And you may see that once it happens, that this simple sound wave, it changes the behavior and it starts bending and it starts refracting. And these are the effects produced by the magnetic field. So we change from one type of the wave to another type of the wave. But on the top of this, it's not only this, but it's also that the magnetic waves that we produce here through this transformation, it's actually much more prone to releasing the magnetic energy than the initial acoustic wave. And this is so because the wave is actually driven now by the magnetic forces. So the magnetic field is very, very strong there. So it makes our charges move in one way, it makes our neutrals move in the other way. And this is what we call plasma neutral drift, when we have different velocities, different relative velocities of the plasma and of this neutral component in the sun. So this is this kind of friction. So remember this metro picture. So this is a friction between the particle, and it produces eventually the dissipation. It produces eventually the friction and the heat that is needed to heat. So this is still being an active investigation. And then another, the first building block of the sun's atmosphere was a convection. So convection, again, it has been modeled since 80s and even before. And the first idealized models, they were looking like what we have here in this picture from the work of Galloway and Weiss of 81, and it already, this picture already picks up all the basic processes that we have in the sun. So if initially we have these like vertical magnetic field lines, then plasma moves these magnetic field lines passively, and it produces this kind of a vortex. And then because of the processes of magnetic diffusion, this magnetic field is expelled from the centers, and you form something which is looking like similarly to this intergranular lane and granular cells, where we have this magnetic course passively moving. But from here, to make it realistic, there are many, many steps. We have to model interaction of plasma and radiation. We need to have realistic equation of state, heat conduction, and moreover, we have to take into account plasma neutral interactions. Then from here to what we do now is this. So this is essentially a process of magnetoconvection. This is a model that we have seen here in this previous slide, but now taking into account all the complex physics, or some of the complex physics that we have in this region. So we have on the left, this is a velocity field, and on the right, this is a corresponding magnetic field evolution in time in one of the models of the solar atmosphere, which is again a very small piece of the sun shown here. And you see the interaction. So all this blinking on the left, for example, we see this is interaction of acoustic shock waves. So this is essentially sound, but the sound moving with a very high speed. So the shock waves, like after the moving plane, they are produced and they are interacting with each other, and they produce all these kind of turbulent motions. And you may find the resemblance also between what we see here and this blue swimming pool movie. So it's actually very, very similar kind of interactions. And the magnetic field, again, it's doing very complex motion. So black and white here means that there is a polarity of magnetic field lines looking toward us and against us, and they again are moving, interacting, and all this is very complex. So we need to extract information from here in a meaningful way. It's also not very easy. And then we also extend these models up to the corona, and what we see is that again, this is a piece of the sun, but now higher up. And we see that this there is a layer where this friction due to neutrals, shown here in green and red color. There is a layer where this friction is actually very, very active. And this is right the layer where we have the chromosphere and the transition and low transition region and low corona. So this is when we have this neutral interaction going on. And again, our model shows us that when we ever keep increasing the resolution in our models, so these heating mechanisms have become even more and more and more important, and there is no stop to it. So in principle, if our numerical models are able to reach even higher resolutions, then we'll probably be able to explain eventually these high chromospheric temperatures in this kind of models and in the sun. And then, of course, like any theory, it also needs an observational confirmation, because, of course, we build up all this complex theory, and we know now that neutrals are important for the dynamics or for the energetics of the solar atmosphere, but we need observational confirmations. And one of the ways to confirm this theory, or to at least see if there are these ion neutral effects acting on the sun, is to measure ion neutral drift, is to measure the relative velocity of the charge component of the ions and of the neutral gas. But for that, you need a very precise measurements, and you need a dedicated observing campaigns, since you need to measure very, very, very frequently, because remember, these partial ionization effects, they happen at very small spatial and temporal scales. And for that, we have been looking at these structures, which are called solar prominences, which is a cloud of solar gas suspended, chromospheric material suspended in the hot corona of the sun. And the advantage of this is because it's being transparent to radiation, and we can be sure that we measure the same volumes of plasma in different spectral lines. So we have been doing observations like this. So to show us here is a live movie of a data that has been taken maybe 10 years ago here on the telescopes of Canary Islands, where we measured these prominences, and we have been using spectra of ionized and neutral lines, neutral helium and ionized calcium. And what we concluded from here is that actually calcium is moving slightly faster. So most of this time they are very, very much coupled. But when we have extreme events like wave crests, or we have strong gradients in space, we see that this black line is slightly, very slightly above the red line. And it means that our calcium, is moving slightly faster than our helium. So this is a kind of effects we are looking at. So this is again is very tentative, and this was one of the first attempts to measure such a thing. And you need to continue this research because you need to disprove if this really is true. But this was already first indication that something might be happening. And the last thing I wanted also to briefly mention is the Evershed effect in sunspots. Evershed effect is an effect that was discovered in India in Kodaikanal Observatory in 1909 by Sir John Evershed. And I've been to this observatory about a year ago visiting India. It was a very interesting experience. Then the Evershed effect consists of an outflow from the sunspot to the outside. So we see again the sunspot that was already shown before. And we see that there is filaments which are penumbral filaments, the gray filaments outside of the sunspot. And if you look closer to it, you may see that the plasma is kind of moving outwards of this dark central region. So this is an outward motion observed at the solar surface. And the reason for this motion is believed to be like a siphon effect. So these are differences in pressure between this dark region, the umbra, and the outside, and it produces this kind of motion. So these are observations which are almost 100 years old. But we wanted to revisit this. So we wanted to revisit it, and in particular, we wanted to see what happens to this Evershed flow as we move higher to the chromosphere, because it has been already known again since very long time ago, 1930, that there is such a thing that the inverse Evershed effect. In the photosphere, we have something, the material that is moving outwards, as these arrows are showing, but as we move higher up, this Evershed effect stops and then it starts moving inside. So there is an outflow material at the surface, but then in the chromosphere, 1,000 kilometers above, it's an inflow. I don't know if it has been explained up to the date. But this is not what concerns me. I wanted to measure this, we wanted to measure this Evershed effect, but now using a lines of neutral and ionized elements. And for that, again, we designed a specific observing campaign where we targeted, I can stop the movie. We targeted a very nice sunspot located to the solar limb, so we can measure this outflow precisely. And this is what this figure is showing us. So we observed this sunspot, and these blue and red colors mean that there is a material moving outside and moving inside. And this is because we see the sunspot tilted. So this is a manifestation of the Evershed effect. And then we measured these velocities, as we see here, Doppler velocities. We measured them using a neutral iron and using the ionized iron. So according to the theories, if these are not entirely coupled by collision, so there must be some very, very little velocity difference between them. But this difference in velocity, again, theoretically, we expect that this difference in velocity should increase with height because the collisional coupling decreases with height. So in the surface, in the photosphere, everything has to be nice and very much coupled. And if we going up, high and high and high and up, so these differences should manifest themselves slightly more. So this work has been done by a master student of us a year ago. And what he did is he performed inversions of the velocities of these iron lines at different heights. So this movie shows us how this height is changing in the photosphere and how these velocities are changing in height. So as we move higher up, so we see that there is this parameter which is called logarithm of the optical depth, and it's moving from positive to negative. Negative means that we are moving higher up. And we see that initially these velocities are very, very much similar, but as we move in higher and higher and higher, we see that slightly, they become different. So the one on the right, which is the ionized iron, it's becoming to be slightly fainter. So in this case, we have slightly slower flows in the ionized iron. And then if we move higher up, you see that at some point, this blue and red changes and becomes red and blue. But it's not the same in both of the lines. So you see that ionized iron become red and blue before the neutral iron, red and black. So this is something that we have seen. We still have no explanation for that because this has not been modeling. But I think this is something that's definitely interesting to pursue in the future. And I hope the student starts his PhD thesis now, and we continue this research in the coming years. And this brings me to my conclusion. So I have some take-home messages. So definitely solar chromosphere is one of the most complicated regions of the sun. The sun creates a reservoir of mechanical energy in the form of convection and waves, which are building blocks of the dynamics of the atmosphere of the sun. And what we do in our research, in my research group, is we search for efficient mechanism to extract energy from this reservoir through the interaction between ions and neutrals. So this plasma neutral friction, this can be such a mechanism. And then theoretical modeling is promising, but observational detection needs large aperture telescope, dedicated efforts, and current instrumentation is very much at the limit. And I leave it here. Thank you very much for listening.
Thank you, Dr. Elena. This was so much information and so interesting. We would like to ask a couple of questions before you leave. Talking about this research that you were just talking of your student, is it the research that he was doing was in the same solar spot than when they first find this Evershed effect? Or it's a different solar spot?
It's a different solar sunspot, yeah. The sunspots, they are very abundant, so you don't need to take all data because, of course, each time you get better and better data.
Mm-hmm.
So the data they got 100 years ago, of course, they didn't have enough quality to this kind of research because it was in India, the telescope was very small, so you need very high spatial resolution for that. So this was a dedicated campaign that we performed here on Canary Islands at the German Tower Telescope few years ago.
That's very interesting. You were even mentioning that we don't really have the big capacity of great solar observatories yet. So what happens once you do the modeling and then you have to go and check the observations? How much does this help you, or how much does it take time of you, because we don't have the necessary technology yet to achieve fast? Or usually how long does it take between the modeling and the observation with the observatories?
Yeah, it's a very good question because sometimes, I mean, I think most frequently at least in the astronomy, we move in the other direction. So we first observe something and then we try to explain, right? Because there is no need to complicate your life because if you can explain something with a simple theory, then why do you need to complicate your life? So here the research goes in the opposite direction. So we first complicated our life, we complicated our theory, and now we try to see if this theory is correct or not. And this is because we first looked in other fields of astrophysics, and there they go the right way. So for example, in molecular clouds, in planetary formation, star formation, they know that these kind of effects are very important because they have observed them.
Yes.
So they know. And then in the sun, we also looked, okay, we also have this kind of plasma. The same kind of plasma. So there must be this kind of effects working. So now we know theoretically that they might be working in the models, at least they're working. But in order to get them in the sun, this is kind of all very indirect because you know that this is a heating, but there are other mechanisms that can produce the heating. So you cannot measure heating directly. So you need to find something that you can actually measure, right? And this is very tricky. So I think we are now at the limit of the instrumentation. We're still trying. I mean, we know that we probably cannot be 100% reliable, but we are trying to perform new observing campaigns to measure something very, very, very fast to compensate this lack of spatial resolution, and to see if we get, at least in these smeared images, if we get some traces of what we get in the theory. Because we have this multi-fluid modeling, we know what kind of velocities we are looking for. So we want to measure them as well. So
It is complex how
yeah.
in a way I find it so amazing how our human minds go beyond and of the questions that we're seeing and we're trying to get answers to, but at the same time our own technology is not ahead enough for us
Yeah.
to help us answer these questions that we're already finding. And in that sense, we have another question. Someone is asking, are there any new observatories coming up that can help observe the sun in the ranges that we actually need? Do you know if there's any
Yeah,
new
there are
project
coming.
coming?
Oh, yeah, there are many projects. So there is very interesting project to be. It's a level of project still that's not yet approved by from US. If if you know how the situation is, but hopefully it will be approved. And these guys are going to measure chromosphere very precisely. So this is right the project for this kind of observation. It's called CIMEX, and this is pushed by High Altitude Observatory in Boulder, Colorado. And there is one mission that's probably fly next year. It's called Muse.
Oh
And
yeah, 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 yeah.
yeah, and I'm going to the conference for this mission right next week, tomorrow.
Oh, it's next
And
week. Oh, amazing.
yeah, and they are going to also to measure chromosphere transition region and corona also very, very, very fast. So I hope there will be this new data. There is an American four-meter telescope, DKIST, which is working there. They still don't have instrumentation for my kind of research, but once they get this multi-level, multi-line capabilities, it can be also done there. And of course, there is this 4-meter European telescope that we are very much pushing in our institute for. So because
Yes.
this one is specifically designed for this kind of observation. So this becomes reality, that will be like what I want, to do.
And I think this is how this is the moment when science starts getting a little bit complicated in a sense that because the instruments that we need it start being so particular and specific, it becomes a little bit hard on having the right tools to actually have them physically to be able to use them with this kind of research that is so specific, but which the ones that I think are one of the most interesting things that we have been hearing about.
Okay. Yeah. It's becoming very, very much specialized, I must say. But we need to go this way. We need telescopes, and we need also the right instrumentation. We need the right instrumentation also for that. Yeah. Okay.
Well, I don't think we have any other questions. Do you have any other comment, Doctor, that you'd like to add to this talk that we shared today?
No, I think I'm good. No, nothing else.
I think this is exactly the kind of talk that we love to have on YouTube because there was so much information that people can just come back and play and stop and do a little bit research on the things that are happening. And this is one of the reasons that we have been enjoying so much this year of Women of Solar Physics, because it has helped us move away a little bit of what we usually talk about in astronomy or planetary sciences. We are able to bring other types of research and try to understand very, very deep, like today, types of multidisciplinary work, which is one of the things that were so interesting because in this sense, we're talking physics, we're talking math, and definitely a lot of things happening. So thank you so much for sharing all of this. We will continue to have discussions with you, I hope, because we usually get many questions after the live event finished because people
Okay.
go
We'll
back
be happy
and
to
have it.
answer. Yeah.
So yes, we will probably you will probably hear from us and having a little bit more questions. Because the idea is that we continue to talk about this type of research and learn a little bit more about everything that you're doing with your own team, and of course with the institutions that you work, which is at the moment of the Astrophysics Institute of the Canary Islands. So I don't know, Naomi, if there's anything else you would like to add.
No, thank you so much, Dr. Elena, for joining us. We are
Thank
so
you for
grateful.
organizing. Yeah.
So we'll go off live now and we'll continue our conversation behind screen. Thank you everyone for joining us, and we are really
Thank
Okay.
you,
grateful for your
everyone.
time.
Have a good
Bye-bye.
night.
Bye.
Thank you. Ciao.